If you're someone who's as passionate about numbers as I am, then you'll find something almost inspirational and amusing with the set of patterns you can form with the Fibonacci numbers. What exactly are the Fibonacci numbers? They are a set of numbers where the next number in the sequence is the sum of the previous two numbers. Depending on different mathematicians, the sequence either starts with a 0 or with a 1. So if we had to list down the first few numbers of the Fibonacci sequence, we'll start with 0 and 1. We'll add up 0 plus 1 gives you 1, 1 plus 1 gives you 2, 2 plus 1 that's 3, 3 plus 2 5, 8, 13, 21, 34, 55 and the list keeps going on. So these Fibonacci numbers do display a really incredible pattern, but you wouldn't expect the squares of these numbers to form a pattern now, would you? Let's check that out as well. So the square of 0 gives you 0, the square of 1 gives you 1, the square of 2 gives you 4, 9, 25, 64, and again the list keeps continuing. Now if you look a little closer, you'll see that 1 plus 1 gives you 2, which is a Fibonacci number. 1 plus 4 gives you 5, which is another Fibonacci number. 4 plus 9, 13, 9 plus 25, 34, and you see that the sum of the squares also give you the Fibonacci number itself. Now let's dig another level deeper. The sum of the first 3 squares gives you 6, the sum of the first 4 squares gives you 15, the first 5 squares gives you 40, and the first 6 squares gives you 104. You don't expect these to be Fibonacci numbers. But if you see closely, the Fibonacci numbers are buried in even these numbers. 6 is basically 2 into 3, 15 is 3 into 5, 40 is 5 into 8, and we see that these are basically the product of the consecutive Fibonacci numbers itself. While these numbers may form really fascinating patterns, what's important to understand is why. Why does the square of 1, 1, 2, 3, 5 and 8 actually add up to 8 by 13? Let's understand this with a simple picture. Let me start by drawing a square of side 1. Alongside that, I'll draw another square with the same side, which gives us a rectangle of size 1 is to 2. Below that, I'll draw a square of size 2, and next to that, I'll draw a square of size 3. You see, I'm drawing squares of the next Fibonacci number as I go along. And these squares will slowly add up to a bigger rectangle. So let me finish that by drawing a square of size 5 and a square of size 8. Now I'll ask you, what is the area of this rectangle? On one hand, it's the base into the height, which is the height of 8, and the base of 8 plus the other square, which is equals a square of size 5, which gives us 8 into the next Fibonacci number, which is 13. On the other hand, the rectangle also is made up of individual smaller squares. So the area of that would just be the area of the smaller squares within it. And that's how we get the square of 1, 1, 2, 3, 5 and 8 equal to 8 by 13. Now if we join the corners of our first square and keep spiraling outwards, we eventually get a spiral that grows at a logarithmic rate. This spiral is a very optimal and widely used spiral and is also called the golden spiral. This spiral continues into bigger and bigger rectangles of size 13, 21, 34 and so on. Now check this out. As the size of our rectangles increase, if we divide the bigger rectangle by the immediate previous smaller rectangle, we approach a ratio known as the golden ratio, which can be approximated to a value of 1.618033. This golden ratio can also be represented by the Greek letter phi and is actually the most irrational number that there is. But what does this golden ratio and golden spiral have anything to do with everyday life? A lot actually. And that's because when we look at nature, we see that so many things flourish when they follow the golden ratio of design. Growing and expanding to the golden ratio rate of spiral allows the maximum amount of rain to be directed to the roots of many plants. Remarkably, you see the golden numbers of 34, 21 and 13 in the most optimal arrangement of sunflower seeds and in the number of petals on flowers. This spiral is the mathematical sequence of tornadoes, of the alignment of our planets, of our Milky Way galaxy,
and dates all the way back to the arrangement of the Great Pyramids of Giza, the design of the Taj Mahal, artistic masterpieces like the Mona Lisa and the Last Supper. In fact, musical legends like Beethoven and Mozart use the golden ratio in timing and pacing of music. Today, the world's most popular brands like Apple, Pepsi, Google have all used the golden ratio in logos and product design. And if you aren't fascinated enough already, let's take this a little closer to home. I want you to hold out your arm and look at the distance from your shoulder to your elbow, and now from your elbow to your fingertips. Pretty crazy, huh? Now, the distance from your fingertips to your wrist is 1, and from your wrist to your elbow is 1.6. It doesn't stop there. The ratio from the furthest tip of your fingers to the bottom of your fingers is 1, and from the bottom of your fingers to your wrist is 1.6. Now check out the spacing of your knuckles. Are you freaked out yet? In fact, mathematicians say that the perfect body and the perfect face follow the dimensions of the golden ratio. But before you pause this video and grab your measuring tape, let's understand what makes the golden ratio so mathematically special.
Now that we've seen the applications of this optimal ratio, let's understand how we mathematically derive it and equate phi to 1.6180 and so on. So let's say we have a sequence, in this case our Fibonacci sequence, where the nth term is actually the sum of the previous two terms, as we've discussed before. Now we know that as our n gets bigger and our limit of n starts approaching infinity, the difference between the ratio of the two numbers starts getting smaller and smaller, until a point where it's so small that it's almost negligible and you can equate the two ratios. Let's assume that the ratio that we're expected to find is called delta. So x of n can also be written as x of n minus 1 plus x of n minus 2 upon x of n minus 1, and that is equal to x of n minus 1 upon x of n minus 2. If we divide our entire equation by x of n minus 1, we get 1 plus x of n minus 2 upon x of n minus 1 is equal to x of n minus 1 upon x of n minus 2. Now if you notice, this is basically just the reciprocal of this. And so we can write this as 1 plus delta, 1 plus 1 over delta is equal to delta. This delta is the ratio we're trying to find, and if we just square up the sides, we'll realize that it's actually a quadratic equation, where you get delta plus 1 is equal to delta square. So delta square minus delta minus 1 is equal to 0. This actually gives us a quadratic equation in the form of ax square plus bx plus c, where x, the root, is actually given by the formula minus b plus minus root 4ac upon 2a. Equating that into our current equation, we get x, which is delta in this case, as 1 plus minus root 5 upon 2. Putting that into a calculator, we get the answer of 1.61803339, which is the golden ratio, and minus 0.61803339. If you notice, then over here we took a general xn term. The Fibonacci sequence is just one of infinitely many sequences where we add up the previous two terms to get the next term. Instead of the Fibonacci sequence, we can take any sequence with any whole numbers or integers or any rational number for that matter, and we will still always get the golden ratio. This is actually where the properties of phi get really interesting. From our quadratic equation, we can go and see that phi square is actually phi plus 1. And this brings out a unique property of phi, which is that it's the only number whose square is 1 greater than the original number itself. So if I ask you to calculate what is 1.618 square, you may need a calculator, or all you can do is just write this as 2.618 ... which is pretty cool because the decimal point of phi stays the same. All you're doing is changing the number before the decimal point. If you think about it, we can also write this as a recursive function. What does that mean? When I say phi square is equal to phi plus 1, I can rewrite that as phi is equal to root 1 plus phi. But then again, phi is also equal to root 1 plus phi. So I can write that as root 1 plus root 1 plus phi. But hey, again, phi is root 1 plus, and that keeps going on. So a recursive variable is basically a variable that's defined in terms of itself. Another property that we can look at is if we rearrange this equation, we basically get phi minus 1 is equal to 1 over phi, which also gives us a really interesting property of phi, which is that it's the only number that is 1 greater than its own inverse. So if I ask you to find the inverse of phi, again, you could use a calculator, or all you could do is subtract 1 from the ratio, which gives you 0.618 and the rest of the decimal places. We can express this recursively as well, where we can basically say that phi is equal to 1 upon 1, 1 plus 1 upon phi. But again, phi is just 1 plus 1 upon 1 plus 1 upon, and that keeps going on. It is actually pretty incredible to see that the most irrational number phi was actually derived from a sequence with 0 and 1 or 1 and 1, the most basic numbers as a start of its sequence. And this sequence actually has such a widespread application in our life, not just in math, but in art, architecture, history, music, and so many other fields. And so before I end this video, I just have a quick teaser for you guys. Like in the Fibonacci sequence, we added the previous two terms to get the next term. What if instead of adding the previous two terms, we added the previous three terms to get the next term? So for example, the first few terms of the sequence would look like 0, 0, 1, 1, 2, 4, 7, and so on. As our n becomes larger, as our number of terms increase, can you calculate based on what we learned the ratio that this new sequence tends towards?